So, welcome. I have a very long title, so this is actually my master's thesis. I'm working at Bielefeld University in a project that is also directly associated with the PhD. And the title of my master's thesis is Design Space Exploration of Associative Memories Using Spiking Neurons with Respect to Neuromorphic Hardware Implementations. So that was all. Probably for those who don't know, I should explain what associative memory is. So the basic idea is that during the training phase, you present the memory an input vector and an output vector. And then in the recall phase, you can present the input vector, and the memory will output the previously trained output vector, even if the input vector is noisy or incomplete. And I'm implementing a special associative memory model that's called Wilshire associative memory model, which is actually quite simple. So all you've got is basically a layer of output neurons, and at the end it's important to state that the input and output vectors are only binary, so only ones and zeros, and the actual content of the memory is stored within the matrix of connections between the input layer and the output layer of neurons. So actually the synapses which you see here, these represent the stored content. Now, the training is also quite simple for those who know it's just sort of heavy in learning, and the synapses are also binary, so either we have a connection with a certain weight or no connection at all. Now, the tricky thing is to have this associative memory working correctly are the neuron parameters. So the output neurons have to exhibit a certain thresholding behavior for the memory to work correctly. And that's where I come in, because now we somehow have to find neuron parameters which somehow are optimal in a sense. And for this, so this is my workflow. What I do, I define some kind of an evaluation method which maps a neuron parameter vector onto a value between 0 and 1, where 0 says these parameters are not good, and 1 says, well, these are nice parameters. Then I use this evaluation function to optimize the neuron parameters. In this case, with respect to certain limitations that the hardware systems, especially the Bielefeld system, exhibits. And once I've done that, I run a complete network simulation for one of these. So I built one of these associative memories and run them on the target platform. So I'm currently mostly using NES for simulation of the network, but it also runs on the Stöckl system from Manchester, and it also runs in emulation on the Obergurgl system, and I hope that I can try it there sometimes in the near future. And the final step is to close the loop and to verify whether the prediction made by the evaluation method actually matches what I had in the actual network simulation. And I also built, to help me visualize these evaluation methods, I also built a tool which allows me to explore this high-dimensional parameter space. So it's like, for the AdX model, it's like 15 parameters, and I can basically view cuts through this high-dimensional parameter space and visualize them in real time, so I can change the parameters, and this program will run a few 10,000 single neuron simulations a second and display such nice images. Okay, that's it. Any questions?